We are in the opening stages of a massive paradigm shift in how we manage and utilize energy. The slow but steady drive to transition away from the consumption of fossil fuels to renewable sources of energy has begun, and from power grids to transportation, this evolution relies heavily on a linchpin group of technologies that store energy. Though most commonly known for its electrochemical variant, a battery or accumulator is a device that stores energy. Batteries fundamentally allow us to decouple energy supply from demand. They can store energy in many forms such as chemical, thermal, or mechanical, and some can even be created at very large scales. For example, the water contained by a dam at a hydroelectric power plant forms a gravity battery, storing energy in the raised mass of water. Stored energy in compressed or heated fluids can also be used as batteries. However, in terms of energy density, cost, and mass producibility, none has been as prolific as the electrochemical battery. Found in virtually every portable consumer device, countless industrial applications, and in most hybrid and full electric vehicles, lithium ion based electrochemical batteries have been at the forefront of practical, energy dense, and easily mass produced rechargeable battery technology for over 20 years. But a far lesser known mechanical based rechargeable battery is showing a resurgence of interest, and it got its commercial start in the 1950s, powering a peculiar Swiss bus. Developed by the Swiss company Oerlikon in the late 1940s, the gyro bus was an electric bus designed to operate quietly along short distance, low traffic routes where installing new traditional overhead trolley power lines was not feasible. What made the gyrobus so unique was that instead of traditional chemical batteries or an internal combustion engine, it was powered by a large 1,500 kilogram flywheel sealed in a low resistance hydrogen filled chamber that spun at up to 3,000 RPM. Energy was transferred into the flywheel by an induction motor, which was powered by three booms mounted to the roof of the bus. The bus would contact overhead charging points along the route, such as at passenger stops, providing up to 500 volts for spinning up the flywheel. To propel the bus, the charging motor would reconfigure as a generator, transforming the rotational energy of the flywheel into electricity, which was subsequently used to drive a traction motor. The traction motor was also used as a regenerative brake, converting the kinetic energy of the wheels back into electricity, powering the flywheel motor, further charging it. These early gyro buses could travel up to 6 kilometers on level ground at up to 60 kilometers per hour on a 3-minute recharge. Idling, the flywheel would remain spinning for up to 10 hours. Later variants deployed in the Belgian Congo were some of the largest examples, carrying up to 90 passengers, though requiring recharging every 2 kilometers. Ultimately, these initial vehicles all suffered from the inability to utilize much of the stored energy, excessive wear, and reliability issues, rendering them too unaffordable to keep in service. The concept of flywheel energy storage was one of man's first forms of storing mechanical energy. The potter's wheel, one of the earliest examples, used the flywheel effect to maintain its energy under its own inertia. Flywheels were also used in water wheels, lathes, hand mills, and other rotary objects powered by both humans and animals. The energy storage characteristics of a flywheel provided a relatively smooth, even source of rotation from the irregular force applied to it. These spinning wheels from the Middle Ages would eventually evolve in the 18th century, replacing their wooden construction with massive single-piece cast iron designs that were mated to steam engines. It was at the onset of the Industrial Revolution that the term flywheel was first coined. With a greater moment of inertia, these heavy flywheels converted the long, forceful reciprocating stroke of a steam engine into smooth, usable rotational energy, quite literally powering the Industrial Revolution. Using flywheels to convert reciprocating motion to rotational force would migrate from steam engines into the next evolution of the engine, the internal combustion engine. From the first three-wheel vehicle built by Carl Benz in 1885 to the technical marvels of modern engines, all internal combustion engines require some form of flywheel to operate. Beyond their pure mechanical use in reciprocating engines, major developments came in the early 20th century when rotor shapes and rotational stresses were thoroughly analyzed, and the flywheel was now being considered as a potential energy storage system. Known as FESS or Flywheel Energy Storage Systems, much like the system used on the gyrobus, these typically use electricity as the working energy. The input energy to a flywheel energy storage system is drawn from an external electrical energy source, such as a power grid. The flywheel speeds up as it stores energy and slows down when it's discharging to deliver the accumulated energy. The rotating flywheel is coupled to an electrical motor generator unit that performs the interchange of electrical energy to mechanical energy and vice versa. The energy storage capacity of a flywheel is primarily determined by its shape and material. Known as the flywheel rotor in most flywheel energy storage systems, its capacity is linearly proportional to the moment of inertia or the resistance to angular acceleration and the square of its angular velocity. In effect, increasing the rotating mass, optimizing the shape, or increasing rotational speed of the rotor allows it to store more energy. In practice, these three properties are constrained by several design factors. The usable rotational speed range of the system is capped by the voltage variation limits of the motor generator system. If the rotor speed drops below a minimum limit, it will produce too low of a voltage when discharging the flywheel rotor, while spinning it too quickly during charging can exceed the torque limits of the motor generator. These limitations of the motor generator system itself will always result in a region of inaccessible storage energy capacity within a flywheel energy storage system. The output power and electrical efficiency of flywheel energy storage systems is implicitly also limited by that of the motor generator. Permanent magnet synchronous motors tend to be the most commonly used electrical machines on flywheel energy storage systems because of their 95.5% efficiency, high power density, and low intrinsic losses. Beyond the motor generator limits, the maximum speed limit at which the flywheel rotor can operate is also determined by the tensile strength of the material it's made from. As the rotor RPM increases and hoop stresses within the rotor exceed the tensile strength limits of the material, the rotor will begin to break apart. The cast iron flywheels used on early steam engines were far too weak for high RPM use. Better performing alloys made of titanium, magnesium, aluminum, and steel were developed, offering up to 20 times more tensile strength. Composites, such as glass fiber and carbon fiber reinforced polymers, pushed flywheel tensile strength even further, easily doubling the capabilities of high-performance metals, though at greater cost. Because the shape of a flywheel rotor affects its moment of inertia, and inherently its energy storage capacity, how efficiently the mass of the material used is utilized is determined by the shape factor of its geometry. Cylinder-based geometries tend to have lower shape factors depending on their wall thicknesses, while solid discs utilize more of the material mass. Lovel disc-shaped rotor geometries approach near-perfect shape factors but are limited to low RPM metal construction. In practice, choosing a flywheel's shape and material is determined by its application, requiring a balancing act between the specific energy or energy per mass and energy density or energy per volume of the flywheel. Automotive applications, for example, might favor energy density as a goal due to packaging requirements, while grid storage systems may focus more on the specific energy. Flywheel energy storage system designs generally fall under one of two strategies: low-speed flywheel systems that operate under 10,000 RPM and high-speed variants that can approach 100,000 RPM. Low-speed flywheels are usually made of heavier, metallic materials and are supported by either mechanical or even non-contact magnetic bearings that support the load with magnetic levitation. High-speed flywheels typically use lighter, stronger composite materials and require magnetic bearings. Because flywheel energy storage systems usually enclose the flywheel within a vacuum to reduce friction, the primary point of energy loss happens at the bearings that support the flywheel. Not only must the bearings support the flywheel, but also resist the forces resulting from its changing orientation, especially the persistent rotation of the Earth. These changes are resisted by the gyroscopic forces exerted by the flywheel's angular momentum, which exerts a force against the bearing system. Traditional mechanical bearings, like those used on the gyrobus, and other simple low-speed flywheel energy storage systems, suffer from high maintenance requirements and a dependence on high-performance lubricants to function. They're particularly sensitive to gyroscopic forces and the friction it generates. Mechanical bearings lose about 5% of a flywheel's total storage capacity per hour. Magnetic bearings, in comparison, have no friction losses and don't require any lubrication, but may require power to energize them in some configurations. Magnetic bearings come in permanent magnet, active magnet, and superconducting magnet variations. Permanent magnet bearings are passive, stiff, low cost, and suffer from low losses due to lack of a flowing current, but this comes at the cost of having limited stability. Permanent magnet bearings tend to be paired with active magnet bearings as a fallback auxiliary bearing in cases of overload or fault. Active magnetic bearings produce their magnetic field from current-carrying coils that control the rotor position. It positions the rotor through a feedback system by applying variable forces which are determined based on the deviation of the rotor position caused by external forces. Active magnetic bearings are high cost systems requiring complicated control mechanisms which consume energy to operate, adding to the overall losses of the bearing system. Magnetic bearing systems are capable of reducing parasitic losses down to about 1% of a flywheel's total storage capacity per hour. Superconducting magnetic bearings provide the best solution for high-speed flywheel energy storage systems, offering compact, frictionless, long-lasting, and stable operation. They stabilize the flywheel without electricity or positioning systems through the Meissner effect, expelling its own magnetic field and creating stable levitation. Superconductive magnetic bearings reduce losses down to well below 0.1% of a flywheel's total storage capacity per hour. However, this incredible efficiency comes at a high cost as they require a cryogenic cooling system in order to maintain superconductivity. Beyond the flywheel rotor, the housing of a flywheel storage system, though static, must be designed with containment in mind. They're generally designed to withstand the forces of the near-vacuum low pressures within the device, as well as be able to contain the energy release of a catastrophic failure of the flywheel. Considerations for the heat generated by the motor generator must also be factored into the design. Some experimental housings even employ a limited or even a full motion gimbal mounting system to reduce losses caused by the gyroscopic effects of the Earth and even from vehicle motion. One of the most attractive characteristics of flywheel energy storage systems are their reliability. They can achieve high cycle lifespans, easily achieving hundreds of thousands of charge-discharge cycles without degrading. They also offer long overall lifespans, easily lasting decades, and typically requiring little to no maintenance. Their charging-discharge performance is also favorable, offering fast response, high energy in-to-out efficiency, and high charge-discharge rates. Their state of charge is also easily measured from rotation speed, and unlike chemical batteries, they are not affected by their life, temperature, or depth of discharge. They also produce no emissions and are easily manufactured from materials not hazardous to the environment. In theory, flywheel energy storage can achieve energy densities far beyond chemical batteries. But in practice, the current state of material sciences limit this, especially in portable use cases. Let's say we wanted to replace a 100 kilogram lithium-ion battery pack in a hybrid vehicle with a flywheel energy storage system. To achieve the 26 kilowatt-hour capacity of the battery pack with a 100 kilogram flywheel, it would need to be 1 meter in diameter and spin at over 37,000 RPM to achieve this. At this speed, the outer edge of the flywheel would be spinning at over 11 times the speed of sound. Packaging and safely containing such an energetic moving component would be cost prohibitive with current materials when compared to chemical batteries for similar performance. Within the limits of current technology, flywheel energy storage systems are more suitable where high bursts of power are needed for short duration. Their power density far exceeds that of chemical batteries, easily supplying hundreds of kilowatts in seconds with little or no degradation at low long-term operating costs. One of the most common uses of flywheel energy storage systems are as uninterruptible power supplies. They excel at providing short-term surge power for data centers, hospitals, and other critical infrastructure sites, costing significantly less than their battery equivalent. Flywheel energy storage systems are also used in a similar manner at the power grid level, providing an energy storage buffer for balancing sudden changes between supply and power consumption. Several grid-level installations offering 2 to 20 megawatts of storage capacity with 15-minute discharge durations have been built throughout the United States and Canada. Demonstration projects based on storing wind power have also been constructed in California. At smaller scales, flywheel energy storage systems have been used where short bursts of power are needed without taxing power supply systems. Notable examples of this are installed at several physics laboratories worldwide, including many fusion experiments, in which megawatt bursts of power are needed to energize electromagnets for a few seconds. The Joint European Torus Plasma Physics experiment, for example, has two 775-ton flywheels that spin at 225 RPM and can deliver up to 400 megawatts of power in the span of a few seconds. Short bursts of power for propulsion provided by flywheel energy storage systems have been used on roller coasters to prevent taxing the local power grid. The electromagnetic aircraft launch system on the Gerald R. Ford class aircraft carriers also use this principle. Each flywheel energy storage system can charge up to 35 kilowatt hours of energy in 45 seconds from the ship's power system and release it all in under 3 seconds, propelling aircraft off its deck. Though a purely mechanical system, the concept for the Flybridge Flywheel Kinetic Energy Recovering System, or KERS, was originally developed by John Hilton and his team when he was technical director of the engine division at Renault F1 in 2006. The now commercial Flybird system uses a continuously variable transmission to recover energy from the drivetrain during braking into a flywheel. The stored energy is then used during acceleration by altering the ratio of the CVT, improving acceleration, and potentially improving fuel economy. The flywheel within the Flybird system can store up to zero point 0.16 kilowatt hours of energy at up to 64,500 RPM in a relatively small, lightweight package. NASA has also experimented with lightweight flywheel energy storage systems for spacecraft with its G2 FESS module design. Designed to spin at up to 60,000 RPM and weighing only 115 kilograms, the carbon fiber and titanium based system is designed to store half a kilowatt hour of energy with a 1 kilowatt charge discharge rate. Although the flywheel is one of the earliest forms of energy storage, flywheel energy storage systems that are compact, reliable, and low maintenance have only been a recent development. As material sciences evolve and more exotic materials, manufacturing processes, and analysis techniques are developed, the future of flywheel energy storage remains very promising, even in a time when the cost of lithium ion and other chemistry battery technologies continue to reduce. With no need for exotic minerals, minimal environmental impact, and unprecedented reliability and longevity, one of man's oldest energy storage systems may prove to be the key to our energy storage future.